Hi there. Welcome to this lecture series on matrix algebra. This is lecture 23, part 2, and the topic is diagonalization of a matrix. So in part 1, we took some examples of diagonalizing a matrix which has distinct eigenvalues and also with multiple eigenvalues but have a whole set of linearly independent eigenvectors. And in this lecture, this second part, we will look into more complicated situations. Okay, let's get started. Let's take our second example with multiple eigenvalues. And as the statement here shows that this will be an example where a matrix cannot be diagonalized. Okay, so let's consider this matrix A and 0, 0, 0 here. So it's upper triangular matrix 3 by 3. And one can write out the characteristic polynomial, which is a polynomial, which is the determinant of A minus lambda I. And you write that matrix out and you see it's upper triangular, and therefore the determinant is just the product of the diagonal. Okay, so which in the end will give us 3 eigenvalues. One is 8 and the other 2 are the same. That's the 2, which is a double eigenvalue. We are now interested in finding the eigenvectors. So for lambda 1, which is 8, which is a single eigenvalue, and the calculation can be done in the similar way that we have done all the time. So we write out this matrix is A minus lambda I, put lambda to be 8, we'll get this matrix times x equals 0. And we see that we can find out a solution V1, which is 1, 0, 0. Okay, so if this is 1 and the other 2 is 0, then the system holds. Now let's look at lambda equals 2, and we set up our system, which is this one. So take a closer look. The third equation always holds because it's 3 zeros times that and add up, it's always 0. And now look at the second equation here, which is 3x3 equals 0. So therefore x3 must be 0. And then once x3 is 0, then you know the first equation becomes 6x1 plus 2x2 is 0. And you can find a solution by picking one of them to be 1 or negative 1. For example, if you choose x1 to be negative 1, then x2 will be 3. And then a scalar multiple of this vector is always also a solution. Okay, and so from the procedure we carried out to figure out this solution, we see that x3 equal to 0 has to be satisfied. And then basically there is one more equation containing x1 and x2 where we could put one arbitrary constant, and then once one is given, the other one follows. So this is actually the only solution, the general solution that we find. Therefore, we can find only one linearly independent eigenvector, actually just one eigenvector. Let's call it V2. Let's take this form. V2 is there, corresponding to the eigenvalue lambda 2 equals 2, which is actually a double eigenvalue. So for this double eigenvalue, we managed to only find one eigenvector. Therefore, we say that the matrix A here does not admit a basis of eigenvectors, meaning it will not have 3 linearly independent eigenvectors, and therefore it cannot be diagonalized. This leads to the discussion on a concept called generalized eigenvectors. So here is a question at this stage we would ask. If a matrix cannot be diagonalized, like in the previous example, then can we still put it in a quotation sign nice form? Something that is still very nice, although not diagonal. Okay, so here's the definition of something called a generalized eigenvector. So let's go through it. So let lambda be an eigenvalue of A. Then a non-zero vector V is the following. So in the first case, this is an eigenvector of A if we have A minus lambda I times V is 0. So that we are familiar with. If it's a solution for that, that is an eigenvector. Second, and this is called a generalized eigenvector of A if we have the following. A minus lambda I k times V equals 0. The k is the power here, which is bigger than 1. And then if this holds, let's say for k equals 2, then this vector V is called a generalized eigenvector of A. So the idea behind this definition is the following. So we want to find a basis V1, V2, Vn of generalized eigenvector, not only the regular one, also the more generalized one. And then we can set this P matrix to be the matrix that contains these eigenvectors as the column. And then P inverse times A times P, and in the favorable case we discussed earlier, this will diagonalize the A matrix, but here it might not be diagonal, but it still will have lots of nice properties. Okay, we'll look into details. Let's continue that second example we had earlier, where we only managed to find one eigenvector. So A is here, lambda 2 is a double eigenvalue, and then we found one eigenvector here. And now we look for a generalized eigenvector, and then we raise up the k, so now k will be 2, so we'll be solving this equation. A minus 2i, 2 is the eigenvalue, square times x equals 0. So you put it in and lambda equals 2, and then multiply this matrix by itself, and you get this one. So you have this matrix times this x vector equals 0 vector. Okay, so we see that now this system here, written out in detail, is like this. So we have this matrix times this vector equals 0. And then we check each equation. So the last equation always holds because they're all 0. And then the second equation also always holds because it's all 0. Basically, we have just one equation coming from the first one, which is 36x1 plus 12x2 is 0. So that is the only constraint. And from this constraint, we can actually find two solutions. So the first one will be actually the V2 that we have already found earlier. If x1 is -1 and x2 is 3, 36 times -1 plus 12 times 3 is 0. So this vector satisfies this equation. And then the second one, which is linearly independent of this one, would be to observe that x3 never occurs in the equation. So we can set x3 to be 1, any constant, and choosing x1 and x2 to be 0, like 0, 0, 1, and this equation also holds. Okay, so we have a V3, the second eigenvector for this eigenvalue, which is 0, 0, 1. And then you can easily verify that these two vectors are linearly independent. So here we would like to point out some connections, some interesting properties. So first, the V2 here is the eigenvector. It's not the generalized one, it's even the regular one. So the regular eigenvector is also a generalized eigenvector. It satisfies this equation as well. And second, and if we look at A minus 2i V3, not with the square on this matrix here, what does that equal to? Well, we can carry out this calculation. We have this is 6 to negative 1. This one here is A minus 2i and times V3, which we have here. And we carry out this calculation, matrix times vector, we'll get this negative 1, 3, 0. And we see that that's exactly V2. So actually these two eigenvectors are connected in this way. Okay, so we can write out. So if we have this, then we can, this relation here, we can multiply this on the left by A minus 2i, another one, then I'll have A minus 2i times A minus 2i V3 would be A minus 2i V2, because this guy here is just V2. And then what is this one? Well, V2 is the eigenvector for a matrix with eigenvalue 2, and that equals 0. So this property that we observed here, actually we show here that it's a general property. Now let's form that matrix P by collecting those three vectors. And I have a 3 by 3 matrix. And the vectors here are linearly independent, so it's invertible matrix. We work out the inverse, which is here. Now we can do a calculation. P inverse times A times P. And we put in the three matrix, P inverse, A, and P. And we carry out this multiplication. We can do this one times that first. Then we get this one, and then we do this one times this one, and we'll get this matrix. And we see that this matrix here is not diagonal, because look at this element that is marked in red color. It is 1, it's not 0, and it's not on the diagonal. And in fact, it is actually just above the diagonal next to the repeated eigenvalues. So 2 and 2, that's the repeated eigenvalue, and the 1 is just above, right next to it. Now let's discuss the concept of multiplicity of an eigenvalue. So the characteristic polynomial, and if you find all the eigenvalues, in general, can be written as the product form like this. Lambda 1 minus lambda to the power m1, lambda 2 minus lambda to the power m2, all the way to lambda k minus lambda to the power mk. So here the powers m1, m2, these are numbers. It could be 1, then it's a single root, and it could be 2, then it will be a double root, or it could be even higher. Then there are two levels of multiplicity of this eigenvalue we would like to define. Let now lambda I be an eigenvalue of A, and we'll have the following definition. We can define the algebraic multiplicity of lambda I, that is the multiplicity mi of lambda I. That is the multiplicity of it as a root to the characteristic polynomial, this pi, this polynomial here. A second multiplicity, we call it geometric multiplicity of lambda I. That would be the dimension of the null space So X is in Cn, and the null space is for A minus lambda I identity. Sorry, I lost an identity. Okay, so A minus lambda I identity times X equals 0. So the dimension of the null space of this matrix here, A minus lambda I identity, is called the geometric multiplicity of that eigenvalue. So what does this number mean, this dimension here? Well, it tells you the maximum number of linearly independent eigenvectors having lambda I as the corresponding eigenvalue. So here is the big theorem that collects all these results. So let's be patient and read through this. So what does the theorem say? So given a matrix A, m by n, then let's say we found all the eigenvalues lambda I. Then for each eigenvalue lambda I, we have the following: 1 less than equal to geometric multiplicity and less than equal to algebraic multiplicity. So the algebraic multiplicity is always bigger than equal to the geometric one, and the geometric one is always bigger equal to 1. And then in the favorable case, if for every eigenvalue lambda I, these multiplicity coincides, that means the geometric multiplicity is the same as the algebraic one, then there is a basis v1, v2, vn of in the space Cn consisting of eigenvectors of A. And then in this case, we can set this P matrix to be the collection of all these eigenvectors, and then the matrix D equal to P inverse times A times P is diagonal. If this doesn't hold, that is, for some eigenvalue lambda I, these multiplicities do not coincide, meaning you have strict less than sign here for some lambda I. Then we can always find the basis v1, v2, vn of Cn consisting of generalized eigenvectors of A, the concept that we talked about this lecture. Okay, so let's take an example. Let's consider matrix A like this, and then we carry out the calculation of the characteristic polynomial, finding the determinant of A minus lambda I, and then we find out that we have this polynomial in a factorized form. And then for lambda 1 equals 8, we have geometric multiplicity is 1 and algebraic multiplicity is 1, and they equal to each other. And for the eigenvalue lambda equal to 2, we find out that the algebraic multiplicity is 2 and the geometric multiplicity is also 2, because we found 2 eigenvectors. So they are equal. And therefore we conclude that the matrix can be diagonalized. Now let's look at example 2, the one we just carried out, looking like this, where we have the characteristic polynomial factorized. And then for lambda 1 equals 8, we see that geometric multiplicity matches algebraic multiplicity, which is 1. But for the other eigenvalue, lambda 2 equal 2, this is a double eigenvalue, so the algebraic multiplicity is 2. But we could find only 1 eigenvectors, so the geometric multiplicity is 1, and we have a strictly less than sign between these two. And then following the theorem, it implies that this matrix cannot be diagonalized. Okay, let's take a third example. Just talk about general ideas. We will not work out the details. So assuming that you have a 6 by 6 matrix and you work out the characteristic polynomial, which can be written in this form after you factorize it. So here you see that lambda 1 equals 2 is a simple root, and then lambda equals 3 is a triple root, and lambda equals 5 is a double root. So we can carry out the calculation to find all the eigenvectors and the generalized eigenvectors. Let's say we can find 6 of them that's linearly independent, and we set the matrix P to be just collecting these vectors. And then we can reduce the A to the following form by doing P inverse times A times P. This one here will take this form. Let's take a closer look at it. So this form here is not diagonal, but it's like almost diagonal. It's at least upper triangular. And on the diagonal, we have the eigenvalues. We have a 2, and then we have 3. It appears 3 times because this is power 3. And then 5 appears twice because this is power 2. And depending on if these vectors are vectors or generalized vectors, in the general setting, there could be a couple of other entries that's not 0. It could be 0 or it might not be. And these will be the entries that's right above the eigenvalues with the multiplicity. So say 5, 5, then this position here might or might not be 0. It might be 0 or it might be 1. And then 3, 3, 3, these are triple eigenvalues. And then the position right above it, so there are 2 of them here. It could be either, they could either be both 0 or they could be, one of them might be 1 or both might be 1, depending. Okay, so we have reached the end of this lecture. In our next lecture, we will talk about powers of matrices and lots of special properties and its connection to eigenvalues and eigenvectors. I hope you enjoyed today's lecture, and I'll see you next time.